Good evening, students. Welcome in next lecture of Math F242 Operation Research. Presently, we are doing game theory. Audio video is okay.
Yes, sir.
Yes, sir.
So let us have this example. Let us have this example from your book. Consider the following two-person zero-sum game. Here we have the two-person zero-sum game. Payoff matrix for the player A is given to you. Here we have the strategy for the player A, and here we have the strategies for the player B, and following are the payoff. Verify the strategies. So we have computed the strategies 1 by 6, 0, 5 by 6 for A, and 49 by 54, 5 by 54, and 0 for B are optimal and determine the value of the game. So we have to we have to check, we have to verify that whether these probabilities are the optimal probability for using the following. Means what is the statement here? If I'm saying that, so means player A should use the strategy 1, right, with probability 1 by 6, and strategy 3 with probability 5 by 6 to get the optimal solution. So first we have to verify. So how we can verify? So here we have we compute the A's pure strategies. A's pure strategy, let's say A1, A2, A3, and B's expected payoff. So how we compute the B's expected payoff for the A's pure strategies? What is the B's expected payoff? Let's say it is the Y1, Y2, Y3, and Y1, Y2, Y3 is given to you as a 49 by 54, 5 by 54, and Y3 as a 0. So for the A's pure strategy, it will become 5y1 plus 5y1 plus 50y2 plus 50y3, y1 plus y2 plus 0.1 y3, right? 10y1 plus 1 y2 plus 10 y3. So when we compute here, you will get the 55 by 6. Second, for the corresponding to a second strategy of the A, it is the 1, and corresponding to A3, it is the 55 by 6. So here we have the 55 by 6, it is 0, 0 or 1. It is 1 and it is 55 by 6, right? So here what we have to compute? Here we have to compute the min max, right? Here we have to compute the max, means here we compute the expected payoff, right? So it will come maximum of this, so it will come the 55 by 6. Similarly, if you take the B's pure strategies, so B1, B2, B3, so here we have the, let's say, x1, x2, x1, x2, and here we have the x3. So expected payoff will become 5x1, 5x1, 1x2, 10x3, corresponding to B1, 50x1 plus 1x2 plus 1x3, corresponding to V2, and corresponding to V3, it will become 50x1, 0.1x2, and 10x3. 10x3. So here we have this. So in this case, if you take the minimum, so here we have the 55 by 6 is the minimum. So you can see here the value of the game will come 55 by 6, right? So actually, whatever we have, the west of the worst for the saddle point, the same thing we are doing for the mixed strategy also, just by computing the expected payoff. Now, in the second part, so that optimal value of the game equal to, this is the another formula for computing the optimal value. Value of the game is nothing, it is the payoff, it is the payoff, right? A's probabilities A is optimal probability and B is optimal probability. B is optimal probability. So if you take the multiple of all three, then you will get the value of the game. That is one formula also, means you can say the value of the game will be, you can verify here. So value of the game will be the payoff into xi into yj into yj. So on solving, you will get the 55 by 6. It is the same whatever the value of the game you have seen from the table. So just for the knowledge, I have uh, I have taken this question, right? So how the value of the game are related to payoff or to the probability. Now the last part. So you have the idea of the linear program from your previous semester course optimization. So how means how we can apply that knowledge to determine the optimal solution of the game, because whatever the method till now, in that we have the limitation that at least one player must have the two strategies only. If both player have the more than the two strategy, then you cannot apply the graphical solution. For some sort, you can apply the dominance rule, but everywhere you cannot apply the dominance rule. So for that, we have to go with the linear program approach. So let us have the payoff matrix for the player A, right? Player A, where player A has the M strategy and player B has the N strategies, and corresponding payoff are given to you. Here A11, A12, A1M, it is 1N, N, right? A21, A22, A2N, AM1, AM2, AMN. So in this case, what is our approach? What is the procedure for the graphical solution? Forget that it must have the means both player must have the, or at least one player must have the two strategy. Forget that. So what is the strategy? What is the procedure? We say let x1, x2, xm are the associated probability for using the strategy a1, a2, am by the player A. Let y1, y2, yn are associated probability with strategies b1, b2, bn used right used by the player B. So if you compute the expected payoff. So what is the expected payoff? Expected payoff corresponding to A1 pure strategies. Age pure strategies. What is the expected payoff? It is the A1 Y1, A12 Y2 plus A1N YN. That is what? Summation of summation of A1J. J vary from 1 to N. Similarly, for this, it will become the A2J. J vary from 1 to N. Similarly, for here we have the AMJ, J is equal to 1 to N. Similarly, corresponding to B's pure strategy, what is the expected payoff? A11 into X1, A21 into X2, AM1 into XM, right? It means you can write it as a summation of A I1 Xi, right? I vary from 1 to M. It is the summation AI2 Xi. I vary from 1 to M. And this is AIN Xi. I vary from 1 to M. 1 to M. Now from here, now means here we have computed the expected payoff a ai1 xi, ai2 xi, ain xi. right? So here we have computed the expected payoff. It means for this means here we have the row. Here we have the row. So for the row, here we compute the row min, and from the row min we compute the max. From the row min we compute the row, means row min, then we compute the max. So that here we have done max of row min of the expected payoff, of the expected payoff, where x1 plus x2 plus xm is equal to 1, because sum of all probability is equal to 1, and all the probabilities are non-negative. All probabilities are non-negative. Similarly, when we have this expected payoff, so in the column first we compute the column max, and corresponding to column max we compute the minimum, means min max of the vertical expected payoff. So this will come, this will come min max of vertical expected payoff, right? And y1 plus y2 plus yn is equal to 1, and where all the yj is greater than equal to 0. Clear this part, because it is very important thing. Anyone, any doubt? Great, I hope there is no doubt. So in this case, if you assume, if you assume let let v is equal to min of summation ai1 xi, summation ai2 xi, and summation ain xi. Let v is equal to this. It means this can be written as, maximum of v, and v is what, minimum of this. If minimum among this, it means when it is the minimum among this, it means all all this are greater than equal to v, right? ai2 xi greater than equal to v, because v is what, minimum among this, and summation ain xi greater than equal to v. So that's we have written in this slide, right? So player A's game problem thus can be written as maximize v subject to, in the in the linear program, on the right side always we write the constant. So it will become, right, and it will, if you take on this side, so v minus summation of ai1 xi, right, less than equal to 0, v minus summation ai2 xi less than equal to 0, v minus summation ain xi less than equal to 0. So that's here we have written v minus summation aij xi less than equal to 0 for j is equal to 1 to n, and x1 plus x2 plus xm is equal to 1, and all xi are non-negative, and v can be positive or negative, means value of the game, either the player a can win or player b can win. So it can be the positive or negative. So v is unrestricted in sign. So that is the linear program, corresponding to player a. Similarly, from here, if you assume let v is equal to what, maximum of summation a1j yj a2j yj and amj yj. So from here you will get minimum of v. From here you will get the minimum of v. Now v is what, v is the maximum of this. It means summation a1j yj less than equal to v, right? A 2j yj less than equal to v, and A mj yj less than equal to v. Or this implies v minus aij yj greater than equal to 0, v minus summation a 2j yj greater than equal to 0, v minus summation a mj yj greater than equal to 0. So from here we have the following linear program for the player B. So minimization of the W is equal to V minus summation of Aij Yj greater than equal to 0 for I is equal to 1 to M, and some Y1 plus Y2 plus Yn is equal to 1, and Yj greater than equal to 0, J is equal to 1 to N. Again, V is what? Value of the game. B can win or B can lose, right? So it can be the positive, it can be the negative. So V is the unrestricted in sign. So these two are constraint. These two constraints are coming from the probability, right? This constraints are coming from the payoff matrix, and here we are writing the objective function, right? And V is the value of game. That's why it is the unrestricted in sign. Yes. Now, any doubt in transforming the payoff matrix into the linear program? Then we have the example. Anything you want to ask here? It is important. Yes, anybody? So hopefully there is no doubt. Let us have this problem. Solve the following game by linear programming. Here we have the A1, A2, A3, right? B1, B2, B3 are the strategies for the player A and player B. So payoff matrix is given to you. Payoff matrix for the player A is given to you. Entries are 3 minus 1 minus 3 minus 2 4 minus 1 minus 5 minus 6 2. So first we have to check whether it is mixed strategy problem or not. So for that, first we compute the row min. So row min for the first part is minus 3 minus 2 minus 6, and column max are 3 4 2. So from this we compute min max, and from this we have to compute the max min, right? So here we have the max min. So you can see min max is not equal to max min, right? Min max is not equal to max min. So we know that value of the game lie between, right? Value of the game lie between the max min to min max. So value of the game lie between minus 2 to 2. So for that, first what we have to do for so now we have to check the dominance rule. If dominance rule is not applicable, it means you cannot apply the graphical solution. If dominance rule is applicable, then you can reduce the size of the payoff, then you can apply the graphical method. If assume that you cannot reduce the matrix, so for that, first we have to associate the probabilities, right? With each strategy, let x1 x2 x3 be associated probability corresponding to strategy a1 a2 a3, such that x1 plus x2 plus x3 is equal to 1, and here y1 y2 y3 are associated probabilities corresponding to pure strategy b1 b2 b3, right? Such that y1 plus y2 plus y3 is equal to 1. So what is the expected payoff? So expected payoff, um, let's say here we have the x1 x2 x3, and here we have the y1 y2 y3, and entries are 3 minus 1 minus 3, 3 minus 1 minus 3, and minus 2 4 minus 1, minus 2 4 minus 1, minus 2 4 minus 1, and minus 5 minus 6 2, minus 5 minus 6 minus 5 minus 6 and 2. So what will be the expected payoff? Expected payoff, right? Expected payoff corresponding to pure strategy a1 a2 a3. So it will become 3y1 minus 1y2 minus 3y3. Corresponding to a2, it is the minus 2y1 4y2 minus 1y3. Then minus 5y1 minus 6y2 plus 2y3. Corresponding to B's pure strategy, what is the expected payoff? Expected payoff for the player A, it will be the 3x1 minus 2x2 minus 5x3, right? Minus x1 plus 4x2 minus 6x3, and minus 3x1 minus x2 plus 2x3, right? So when we have this, so over this we have to means now this is the column. So first we have to compute the column max, and for the column max we have to compute the min, right? Min of these. For the row we have to compute first row min, and for the row min we have to compute the max. It means the value of the game will be, or you can say we have the min of max of 3y1 minus y2 minus 3y3 minus 2y1 plus 4y2 minus y3, and minus 5y1 minus 6y2 plus 2y3, right? 2 by 3, or max of min of 3x1 minus 2x2 minus 5x3, minus x1 plus 4x2 minus 6x3, and here minus 3x1 minus x2 plus 2x3, right? So here we have this. So what I have told you, let us solve the first one. So let's say let v is equal to max of 3y1 minus y2 minus 3y3 minus 2y1 plus 4y2 minus y3, and minus 5y1 minus 6y2 plus 2y3, 2 by 3, right? So problem will become linear lpp will become minimum of v, and from here what the result we have? From here the result is what? V is what? Maximum of all these means all are all are less than all are less than equal to v, right? Minus 2y1 plus 4y2 minus y3 less than equal to v, and minus y3 minus 5y1 minus 6y2 plus 2y3 less than equal to v. And we know that never we write the variable on the left on the right side, so this will give you v minus 3y1 plus y2 3 plus 3y3 3y3 greater than equal to 0. This will give you v minus or v plus 2y1 minus 4y2 plus y3 greater than equal to 0, and this will give you v plus 5y1 plus 6y2 minus 2y3 greater than equal to 0, where y1 y2 y3 are what probabilities. So y1 plus y2 plus y3 is equal to 1, and since it is the probability, so y1 y2 y3 greater than equal to 0, non-negative. And we know that value of the game is what, it is the value, it can be positive or negative, so v can, or 0 fair game, then it is the 0. So v is unrestricted in sign. Unrestricted, it is the unrestricted in sign. Unrestricted in sign, generally we say urs, right? V is urs. So this is the lp linear program for the given problem. So here we have the linear program for the given problem. Clear? So when we apply the simplex method, at that time you will get the y1 as a 0.32, y2 is 0.08, y3 is a 0.60, and value of the game will come minus 0.91. Minus 0.191 means if payoff matrix is given for the player A, it means B is winning by the amount 0.91. A is losing by the amount 0.91 and B is winning by the amount 0.y1. So similarly, if you want to write the problem, from this, right? If you want to write the problem from this, so here we have to assume let v is equal to what? V is equal to minimum of 3x1 minus 2x2 minus 5x3 minus x1 plus 4x2 minus 6x3 and minus 3x1 minus 3x1 minus x2 plus 2x3 minus x2 plus 2x3. If you assume this, so what it will give you? It will give you the problem maximize v, right? Because here we have the maxmin. So it will be the maximum of v, and from here what the result we can say, if v is the minimum of all these, means all are greater than v, all are greater than v, means 3x1 minus 2x2 minus 5x3 greater than v, minus x1 plus 4x2 minus 6x3 greater than equal to v, and minus 3x1 minus x2 plus 2x3 greater than equal to v. So you know that on one side always we have to write the constant. So this will become v minus 3x1 plus 2x2 plus 5x3 less than equal to 0. This will give you v minus v plus x1 minus 4x2 plus 6x3 less than equal to 0, v minus or v plus 3x1 plus x2 minus 2x3 less than equal to 0. And since x1, x2, x3 are the probabilities, so x1 plus x2 plus x3 is equal to 1, and they are non-negative, and value of the game is unrestricted inside. So in this way we can write the player A game. So here we have the player A linear program. Maximize v minus 3x1 plus 2x2 plus 5x3 less than equal to 0. And for second constraint, third constraint, fourth constraint, then we have the non-negativity and unrestricted. So here when we apply the simplex method, so here it will be the x1, x2, x3 like this, and v will be the but either you solve the player A problem or player B problem, you will get the same answer, right? So from here you can conclude one thing about the linear program for the player A and player B. Can you can you say something from these two LP?
Sir, one is the dual of the other.
Yes, one is dual of the other. Means if you have the optimal solution of one, using that duality you can determine the other solution, right? Means LP of player A is dual of LP of the player B, right? So using the theory of the duality, you can determine the optimal solution from the optimal solution of any one player. Clear? Is there any doubt? Anything you want to ask here?
Sir,
Huh?
so V is negative. That means A is losing, right?
Huh, A is losing.
Okay, sir.
Value of the game from the both. Either you solve by the player A problem or player B problem. Value of the game will be the same. Any other doubt? So let us have this problem, right? Let us have a player A payoff matrix, and player A have the three strategies, and player B has also three strategies. And this is the payoff matrix. So payoff matrix is given to you: 1 minus 1 3, 3 5 minus 3, right? 6 2 minus 2. So first we have to verify whether it is the problem of mixed strategy or not. So for that, first we compute the row mean. Row mean is coming minus 1, minus 3, minus 2. Column max is coming 6, 5, 3 respectively. So from that we compute min max, and here we compute the max min. So max min is coming minus 1, min max is coming 3. So you can say that since min max is not equal to max min max is not equal to max min, then it is the mixed strategy problem. And the value of the game always lie between these two. So value of the game lie between the minus 1 to 3. Then let's say let's say x1, x2, x3, y1, y2, y3 are associated probability corresponding to pure strategies a1, a2, a3, b1, b2, b3 respectively, such that x1 plus x2 plus x3 is equal to 1, y1 plus y2 plus y3 is equal to 1. That always you have to write, right? Always you have to write about the xi and yj, right? So when when A is using the pure strategy A1, then B's expected payoff will become, right? B's expected payoff will become y1 minus y2 plus 3 by 3. Now you have the enough idea, you can write directly. Corresponding to A2, the expected B's payoff will become 3y1 plus 5 by 2 minus 3 by 3, and corresponding to A3, pure strategy of player A, B's expected payoff will become 6y1 plus 5 by 2 plus 2y2 minus 2y3. So here we are writing the expected payoff in this column, right? In the column. Then when we are using the B's pure strategy, then what will be the age expected payoff? So corresponding to B's pure strategy, B1, B2, B3, age expected payoff will become, age expected payoff will become the 1x1 plus 3x2 plus 6x3 minus x1 plus 5x2 plus 2x3, 3x1 minus x 3x2 minus 2x3, right? So here we have the this. So here we are writing the expected payoff, right? Expected payoff as a row, right? Expected payoff as a row. So in this we have to compute first row min, then we have to compute its max. In the column we have to compute the column max, then we compute the min max, right? So that's only we will do here. So v is what? V is the min of max of, actually it is only the v, right? Because min max is equal to max min is equal to v only. So v is what? Minimum of max of this, and v is here max of min of these. So when we are writing the player A problem, or first we write the player B problem. So when we write the player B problem, so from here what we are doing? We are minimizing the v, right? We are minimizing the v. So minimize z is equal to v. What is the v? V is the max of these three. So when v is the max of these three, it means v is greater than equal to all these three. So we write y1 minus y2 minus 3y3 less than equal to v. 3y1 plus 5y2 minus 3y3 less than equal to v. 6y1 plus 2y2 minus 2y3 less than equal to v. And since it is a probability, so we write the y1 plus y2 plus y3 is equal to 1, and v is the urs, y1 plus y2 plus y3 greater than equal to 0. Similarly, if you have to write the LP problem for the player A, so for the player A, here you are maximizing the V. So maximize V, where V is what? V is the minimum of these three. So when V is minimum of these three means all are greater than equal to V. So here we are writing that x1 plus 3x2 plus 6x3 greater than equal to V, minus x1 plus 5x2 plus 2x3 greater than equal to v, 3x1 minus 3x2 minus 2x3 greater than equal to v, and x1 plus x2 plus x3 is equal to 1. V is urs, and x1 x2 x3 are non-negative. So now our our duty is to solve these LPs, right? These two are dual of each other. These two are dual of each other. Presently direct form I have written, but when we have to solve at that time, we have to write the constant on the other one side and all the variable on one side. So when we want to solve the for the player A, so solution for the player A problem will become, right? So maximize z is equal to v, right? And we take all the variable on one side, so it will become v minus x1 minus 3x2 minus 6x3 less than equal to 0. Means when we ask write the LP, you have to write in this form only, in the standard form. It is the standard form. V plus x1 minus 5x2 minus 2x3 less than equal to 0. V minus 3x1 plus 3x2 plus 2x3 less than equal to 0. x1 plus x2 plus x3 is equal to 1, and v is urs x1 x2 x3 greater than equal to 0. It means how many decision variable presently we have in the, now forget what is the game. Now you see it is the LP. So how many decision variable we have presently? Yes, number of decision variables. 4, x1, x2, x3 and v, right? And how many constants we have? How many constants we have? That is also 4, v minus v plus v minus x1 plus x2 plus x3 is equal to 1. So we have the 4, right? We have the 4 constants and 4 variable. Out of the 4 variable, one is the urs. So when v is the urs, when v is urs, you know that we tackle this as a v1 minus v2, right? We can write the vrs as a v1 minus v2 such that v1 and v2 are non-negative, right? I am not going in the means I am not going to explain the simplex method, right? You have enough idea about the simplex method. So you know that here we have the is equal to, so we require one artificial variable, let's say r9, and this is what, this is a less than equal to, so here we write the slack variable. So slack variable we are using as a, it is the x3, so it is the s6, s7 and s8. These are the slack variable, and in the last one you have to use the artificial variable. So when we have the artificial variable, we have the two methods, either the begin method or the two-phase method. So when you solve the two-phase method, so for the two-phase in two-phase method, for phase one, always we minimize the sum of the artificial variable. So minimization of the r9. So minimization of the r9. So here we have taken the r. So here we have the table, right? We are writing all the variable, right, as a heading v1 v2 x1 x2 x3 s6 s7 s8 r9, and on the right hand side we have the solution. So from the objective function we have the 0 0 0, last is the -1, then the solution is 0, right? Then since s6 s7 s8 s9 are the initial basic feasible solution, right? It is the initial basic feasible solution. So table must be the consistent. So for making the consistent means this entry must be the 0. This entry must be 0. So for making the it 0, what we are doing, we are adding this row with the row of r9. So due to that we have the following change in the table. So it will come 0 0 1 1 1 0 0 0 and 0, and on the right hand side we have the 1. Then apply the simplex method. So here we have the second table, right? Here we have the second table, here we have the third table. In the third table you can observe that r is coming 0. It means it is the optimal table. It is optimal table for the phase 1, right? It is the optimal table for the phase 1. So here from the phase 1, after the optimal table of the phase 1, we write the we write the objective function. We write the objective function for the original problem. So for the original problem is what, right? Original problem is what, maximize of the v. So maximize of the v means it will be it will change, it will change to -1, it will change to 1, v1 minus v2, and um, right, and all other will be the 0, right? 0 0 0 0 0, and here we can drop this column, we can drop this column, and on the right hand side, on the right hand side it will be the 0, right? It will be the 0. Now this is the corresponding to Z. Whatever the whatever our Z that we have introduced, means from here we have started the phase second, and here we have the phase one. Right here we have the phase one. So for the phase two, for the phase two, here the entries are, right, this is with the 0 0 0 1 0. Then here we have the 0 0 0 -1 0. Here we have 0 0 1 0 0. Then here we have 0 0 0 0 1. Then here we have 1 -4.67.33. Then 1.0 and 0.67. Here we have the 0 1 0 0 0. Here we have the point 0.5 -0.67. It is the 0.08.50 and -0.08. And here we have the 0.50. So here we have the -0.33 -0.08.50 and 0.08. Right. And on the right hand side, right, and this column you have already dropped, so for corresponding to this column no entry will come. Right, corresponding to this column no entry will come. And on the right hand side we have 1.67.1 and 0.33. So it is what? It is the 2 by 3. It is the 1 by 3. So from here you can say x1 is what? 2 by 3. x2 is 2 by x1 is 2 by 3, and x2 is what? x2 is 1 by 3, and automatically x3 is not in the answer, so it is 0. And value of the game will be here. So value of the game is 1. Value of the game is 1. And from the optimal table you can determine directly the solution for the, right, solution for the dual problem also. So here these are the solution for the dual variable, right? So it is the y1, y2, y3. So this will give you y1 is equal to 0, y2 is equal to 0.5, and y3 is equal to 0.5, and value of the game is equal to 1. So in this way you can solve the from the player A you can write the optimal table for the player B, means optimal solution for the player B also. So this is the, means, simplex method, means you can solve. So please revise how to solve the, means how to apply the simplex method. But in this, what the problem you have faced? Last thing I have to explain. What the problem you have faced? First, we have to introduce the artificial variable. Then we have to go with the two-phase method, right? Even we have to tackle with the unrestricted sign. right? We have to tackle with the unrestricted sign. So I think it is the 750. Next class we continue better. Yes, it's better, or I should continue? No response? Yeah.
Sir, do it in next class.
I think it is. It takes around 20 minutes, so it's better. Next class we continue. So this is the last topic, right? So in next class I will start the new chapter also. So that's all from my side for today. Meanwhile, please revise the simplex method. How to make the table, because in this course I cannot explain the how to make the table.
Sir, do we need to revise all the three, like generalized simplex, dual simplex, all of them, or
No, only the simplex method. Only the simplex or two phase big M method जो है ना, not
okay,
that. फर्स्ट मतलब जो चैप्टर 3 है, आई थिंक उस बुक का चैप्टर 3 है, कहा
okay,
वाली बुक में चैप्टर, ठीक है ना, तो दैट चैप्टर ओनली. No need to remember the duality. Duality directly you can write from the table, right? Means whatever the z coefficient of the slack variable, that will give the optimal solution of the dual variable. So from that you can write. Any other doubt?